Now, let's pick from current slide and go. Couple of things announcement-wise. This is nearing the end of Cougar Connection Week. Two sets of activities today, and one of them is right here in front of us. This is induction day for ambassadors, several of the other groups, Phi Beta Lambda, or some of the different groups. I can't remember all the names, honoraries and things like this. So Student Government Association officers, that kind of thing. That's happening at 1 o'clock this afternoon on the Birmingham East Campus in the A.G. Gaston Auditorium. And all are welcome to come. They're your representatives. They're your classmates. Come and see the induction ceremonies, and maybe it'll prompt you to say, I think I could do that, so please go support your classmates, okay? Of course, Dimitri is already in, so he's one of the existing ones going to be part of the induction of the new ones. Okay, and you're ambassador, right? Mm-hmm. Yeah, okay. Now, then, later this afternoon from 4 to 6, over on the West Campus, Birmingham West Campus, in the Arthur Shores Fine Arts Building, is our swimming pool. Don't you normally put swimming pools in fine arts buildings? Yes, okay. Actually, it's also our gymnasium, the weight room, all sorts of things are there. It's just a big building, and the indoor pool, great facility, is in the back. I'm sure there's going to be some good music. I'm sure there's probably going to be some good food, and there will be opportunity to participate in the pool if you want to, but not if you don't want to. But it should be a good time. That's 4 to 6 this afternoon. It's kind of the official close of Cougar Connection Week. With one little exception, I think they are scheduling the Red Cross blood drive next week sometime. Is that right? Okay. So that they couldn't get it scheduled this week, so it's going to be next week. All right. Anything else? Yes. There are 2 requests for assistance, okay? One is for note takers, okay? A few years ago, I had in my physical science class a really bright kid, but he had pretty severe cerebral palsy in a motorized wheelchair, and he could not, his hands didn't operate well enough to take notes. So our Office of Disability Services provided note takers for him. At least most of the time. Sometimes they didn't show up, and students would help cover for him, take notes for him. But there are always those needs. They will pay you. It's not just volunteer, though that would be nice. They will pay you to take notes. And the request came from the Birmingham West Campus. I assume that's where it is, but it could be on either campus. So if you are interested in doing that, please let someone know. It's Miss Janine Jones. That's jjones@lawsonstate.edu. Okay? Another, not same type thing, but a little bit similar, is the fact that the Space Center, and especially the one on the Birmingham campus, is looking for tutors. And if you are pretty good in math, yes, many of you are, English, I think, biology, Spanish, computer science, there's a bunch of, at least 5 disciplines they need tutors, and they will pay you for that. It's not free, okay? It's free for the students, but the Space Center is a federal program that they provide the funding for it. And so you, the tutor, gets paid. So if you'd like to participate in that, it's Miss Leslie Harper, who's normally on the Birmingham campus as well. And JT is usually here, okay, and he is today. So if you are interested in tutoring any of those subjects or just checking it out. We do have a Space Center on this campus too, and I bet you he would love to know if there's some tutors available as well. Also, Student Support Services right across the hall. Actually, the main office is down around the corner here, but they also look for peer tutors. So you can make some money while you're on campus, in between classes, at your convenience, and help other students. Win-win-win situation. Oh, the third win, how I learned math the best was not by studying to do well on a test, though that helped, okay? But it was when I was tutoring someone and having to explain to somebody else why the math worked. I had to know it way better, and that helped me big time do well in math. And that would work in any other subject as well, so it will also help you. That's the third win. All right, besides the money, okay? It helps you with the thing. Any questions on anything we've done so far? Sorry that took too long and had the delays because of the thing. I was thinking as I walked down the hall, I wondered if heat was an issue here, that it has to sort of warm up and then connections get better. That might be it. I don't know, because it happened sort of this way yesterday one time too, but it's enough of that. All right, here is example 2, and unfortunately, they've already done most of the work for you, okay? Here's the graph of a function. F of x is equal to x to the 4th, okay? It says write an equation for the function represented by each of the next 2 graphs, okay? So here's f of x is equal to x to the 4th. What does that look a lot like? Okay, you were already here, but you want to here? Okay. Got it. Okay. Anyone else come in since I called roll? Okay, what does that look a lot like? Any other we've seen? Yes, it looks a lot like x squared, okay? But this is x to the 4th. Now, what are some of the differences? And they're pretty subtle, so I don't know if you can pick them up. But here, yeah. Okay, yes. It's flatter at the base, and it's also steeper on the sides. You probably can't tell the steepness on the sides, but if you think about it, 0, 0, certainly a point on both of them. And 1, 1 will be a point, and negative 1, 1 will be a point on both of them. Okay, those will be the same. This is flatter here. But when you get to 2, if this was x squared, that would go up to 4. X 4th would go up to, ooh, I hear the gears grinding. Okay? 16. Okay? So yeah, much steeper on the outside. Flatter on the near 0, steeper outside, plus and minus 1. Okay? Plus 1 and minus 1 on the x-axis. So yeah, that looks a lot like the squaring function. It's the quartic function, you might say. Okay? Now, that's what, wanted to get that firmly planted in your head. That's what that one looks like. Now let's see 2 other graphs. Now write equations for the graphs below as a transformation of the graph of f that we just saw. Okay? What do you reckon this one is? Okay? Now, just to get you an idea, here's minus 1, 0, 1, 2. Okay? What do you reckon has happened to G, happened to F to make G? Any ideas? Second? I heard something. What has happened to F? Remember how F looked? Okay, say that again. Reflected, and how do you indicate the reflection? Negative f of x, which would have been negative x to the 4th, and then what's this upward shift? Plus 2, that's it, right there. Negative x to the 4th, that flips it over, plus 2, that raises it up. Okay? Make sense? How about the next one? Okay? Okay? You're right to think that something's happened to the x, and it went to the right 3 times. What? Yes, you're adding or subtracting, not multiplying. So that was 1. And how does that work for the x? Second? Yes, exactly. Remember, everything on the x-axis is backwards. So since it moved to the right, that'll be x minus 3. And you also had a else happened from the first one? Remember the first one? Yeah, you also have the negative. So it's minus, in parentheses, x minus 3 to the fourth power. Does that make sense? Okay? So let's get those written down, and then we'll see how they did. Okay? Get my pen out. Okay? This one would be, let me get my pen color. Okay, what's that noise? Okay. I'm worried about everything now. So this one would be g of x would be, as you indicated, minus x to the fourth, minus f of x. That flips it over, and then you add 2. That was it exactly on that one. On this one, your h of x, okay, you've got the minus, but now you have a horizontal shift, and shift is a plus or a minus, and that happens to be an x minus 3, now raised to the fourth power. Still, the basic function is the fourth power, okay? But the negation flips it over, and the x minus 3 shifts it to the right 3. Does that make sense? Okay? Any questions on it? All right. Let's see how they did it. The graph of g is a reflection in the x-axis followed by an upward shift of 2 units for the graph of y, f of x equal x to the fourth. So that would be, just like we said, negative x to the fourth. That's the reflection. Then the plus 2. The shift upward. Okay? Make sense? The B one, the graph of h is a horizontal shift, 3 units to the right, followed by a reflection in the x-axis. Guess what? You can reflect first and then do it. The first one, you do reflect first and then shift up. If you shift up first, then you reflect about x equal 2. Okay, I mean y is equal to 2. And that's a little more awkward. So it's better on the first one to reflect first and then shift upward. This one, it doesn't matter. You don't have to horizontal shift first and then reflect. You could reflect first and then do a horizontal shift. Either one. Both of those will work there. So in that case, either case, h of x is minus the x minus 3. That's your horizontal shift raised to the fourth power. Now, the reason they said do that first is you put that in parentheses, and you usually do that first. What's parenthetical, then you change your sign. But it really doesn't matter which one you really do there. Any questions on those? Very good. All right, there is a checkpoint, bottom of the page. Good idea to do the checkpoint as soon as you get out of class, either this class or your next class or whatever. When you have some free time, try to get the checkpoints done sooner rather than later. All right, let's go to reflecting graphs. Okay? We've been doing reflecting graphs. When sketching the graphs of functions involving square roots, okay, remember you must restrict the domain to exclude negative numbers inside the radicals, okay? It's not just the x, it's whatever the entity inside the radical cannot be negative. It has to be greater than or equal to 0. So here's a few examples of that. And actually, they do this after example 3, which they skip completely. So let's go back and do example 3. All right, we'll do it here. Compare the graph of each function to the graph of f of x is equal to the square root of x. Okay? So I'm going to first graph f of x is equal to the square root of x. No, you're going to graph it. Okay? Okay. Give me some points to put on f of x equals square root of x. That function up there. Give me some points. Second? 0, 0. She picked mine. Okay. Next. Help me. Y'all did this parent function. What is it? Another point. Give me an x. 4. Okay. There's 4. Where do I go now? Square root of 4 is 2. Okay, so I go up 2. All right, there's another point. Any others? Give me another x. Second. Ooh, okay. What's the square root of negative 4? You can't do it. Undefined, okay? But there is another easy one. Not quite as easy as 0, 0, but almost. Yo, goodness gracious, what are you doing? Oh, come on now. I don't know what it's going to do if I say keep. Okay, I think it's going to try to write that. And it won't. It shouldn't write it. So let's go back to where we were. Current slide. Ah, look at that. It is still here. Okay. Give me another point. Give me another x. 1. Okay, and what's your y then? Also, ooh, it changed my color though, didn't it? Okay, that will also be 1. Now, if we had another one, I'd go out to 9, but we don't. 1, 2, 3, 4, 5, 6, 7. Somewhere out there's another one, and here's what, ooh, I can't draw. Here's what that function looks like. Okay? Something like that. That's the square root function. Remember what we called it? Half of a sleeping parabola, right? Okay. Kind of that. Okay, I don't have it smooth enough down here. It should be more rounded there. Okay. All right. So there's our f of x. That's the parent function. Okay? We're going to now do g. So I need another color for g. Pick a color, any color. Second? Red. Okay? And here's what g is. G is equal to negative square root of x. G of x is equal to negative the square root of x. What in the world does that do to the f? What does that do to the f? Second, reflects it across what? The x-axis. You're absolutely right. It negates it. So 0 stays 0, but now the 1 up here, the y value 1 here, becomes a negative 1 here. And the y negative, positive 2 here becomes a y of negative 2 here. So that is an exact reflection across the y-axis. There's your g of x. All right? Now, I need another color. Green, okay? Light or dark? Okay, I'll go with the dark. I couldn't hear what you said, but I'll go with dark. This will be h of x is equal to the square root of negative x. H of x is equal to the square root of negative x. Whoo! I get chills when I see that. Why? Can you do that? Why not? Okay, but what if x were negative? Oh, yes, x could be negative. So what this does, see, this one didn't change our domain at all. What was in the radical was still had to be greater than or equal to 0. But this one, what's in the radical has to be greater than or equal to 0. And if minus x is greater than or equal to 0, guess what x is? Less than or equal to 0. Your name, please? Trace. Okay, Trace. Okay. I know you're here. You are. Okay. All right. So this changes our domain. We're over there now because the x has to be less than or equal to 0. All right, for that to work. So, give me some points. So 0, 0 is still there, and negative 1 1 will still work, and negative 4, 2 will work. So here is our graph there. That's a reflection across the y-axis, right? We negated the x, so it reflects across the y. Whatever your x was positive on the first, now that same negative x works on the second. Exact reflection. Okay? And then the k of x. All right, I need another color. What? Blue. Okay, let's go with blue. And this is our k of x. K of x is equal to, then minus the square root of x plus 2. Minus the square root of x plus 2. Tell me what's happening there.
It's the same with the g of x, but you move over 2.
Okay, which way?
To the right.
Ooh.
Or to the left.
Yeah, because it's an x. You go backwards, remember? Okay, so your 0 here moves 2 to the left. There's your 0 there. Okay? Your 1 up here, always go back to the parent function. Your 1 up here moves to the left 2, but does what? We didn't take care of the minus sign because 0 minus 0 is still 0, okay? But when you have you shift 2 here to the left, but then you go reflect across the x-axis because you negated your y here, right? So that moves it down there. And then your 4 here shifted 2 to the left, that goes over here to 2, and shifts down and reflects down to minus 2. So here is that graph, sort of, okay? Now, notice what happened to your domains on those. On the first one, domain was exactly the same. X was your parent function, x has to be greater than or equal to 0. Here, same thing's under the radical, x has to be greater than or equal to 0. Here, because it's a negative x, has to be less than or equal to 0, because negative x has to be greater than or equal to 0. When you divide or multiply by minus 1, you flip the direction of the inequality. It's hard to see up there, isn't it? And then the k of x, now your x plus 2 has to be greater than or equal to 0. Let me write that down. This is how we do our domains. What's under the radical has to be greater than or equal to 0. Then subtract 2 from both sides, and you have x is greater than or equal to negative 2. Adding or subtracting a constant does not change the direction of the inequality. That stays the same. Multiplying or dividing by a positive number doesn't change it. It's only multiplying or dividing by a negative number like we had up there that flips it. So here we have x is greater than or equal to negative 2. There's our x's. So that function looks good. Does that make sense? Any questions? Let's see. I think we could have plotted our third point here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, that would have been negative 3 down here. So if I had done that, it goes down a little further. Okay, but it's all right. You got the general idea. Any questions on that? That one wasn't on the slide set, so I can't show you what the book does with it. Okay, any questions there? All right, let's move on to what they were saying here. When sketching the graphs of functions involving square roots, remember you must restrict the domain to exclude negative numbers inside the radical. A lot of people think it's only dealing with x. No, it's what the expression is inside the radical. And we just did this. Something like it. Yeah, we did exactly this. When your expression inside was x, even though it's a minus on the outside, who cares? It's what's inside the radical. Okay? That has to be greater than or equal to 0, just like we saw. But if it's a minus x in there, minus x has to be greater than or equal to 0, which means x has to be less than or equal to 0. Because you multiply by minus 1, which flips the direction of the inequality. On This one, your x plus 2 has to be greater than or equal to 0. When you subtract 2 from both sides, it gives you x greater than or equal to negative 2. Make sense? And you see our graphs, what we did with it, it mirrored the same activities. Any questions? All right. Now, up till now, we've been doing what they call rigid transformations. If you have a parabola, everything we've been doing, shifted it up, down, right, left, both directions, flipped it, the shape of the parabola stayed exactly the same. Now we're going to do some non-rigid transformations, and Cody's been wanting to do these because he wanted to multiply by 2 earlier, or 3, or something like that. Okay, so now we're going to deal with non-rigid transformations. The horizontal shifts, the vertical shifts, and reflections are all rigid transformations because the basic shape of the graph is unchanged. The direction is changed, the position is changed, but the basic shape is not changed. Those transformations change only the position of the graph in the coordinate plane. They don't change the relative shape. The non-rigid transformations are those that do cause a distortion. This could be a stretching or a shrinking, either horizontally or vertically. Okay? So let's take a look at what that. For instance, a non-rigid transformation of the graph, y is equal to f of x, is represented by g of x is equal to c times f of x. Now, if c is 1, that's no transformation at all. You know, it's the same function. But c could be greater than 1, or c could be between 0 and 1. We're not going to get into negative numbers. Okay? And we never have c equal 0. Why not? Zero times f of x would be 0. And that wouldn't be a very interesting function, would it? It would just be nothing. Okay? So it loses everything. So don't ever multiply by 0. Ever. Not a good idea. And definitely never divide by 0. Ever. Okay. But, okay. Any c greater than 1 or between 0 and 1, but not 0. Okay. Another non-rigid transformation of the graph is represented by h of x equal to f of cx. Now you're multiplying. Okay, now think of this one. This one. Okay. Remind me what f of x is? Y, always. Okay, remember that. Here we're multiplying the constant by the y. Okay? So that would indicate we're stretching or compressing, shrinking the y value. Okay? Here, we're multiplying the c by the x. So that means we're either going to shrink or stretch horizontally. Unfortunately, I do too much stretching horizontally. Okay, but we won't get into that. Okay, the transformation is okay. Now here's the deal. I forgot to read the rest of this. If your c is positive, is greater than 1, of course, that's a vertical stretch. Any y value you had here, if you multiply that by c, and c is greater than 1, your g value is going to be bigger, right? Okay, so that's a vertical stretch if c is greater than 1. If c is between 0 and 1, that's a shrink because you're multiplying by a number that's less than 1 but greater than 0. So that's a vertical stretch. Guess what happens with the x's? Backwards. Everything to do with x is backwards. If the c is greater than 1, you have a horizontal shrink. If the c is between 0 and 1, you have a horizontal stretch. Makes no sense until you actually play with it some and see it's got to be that way. Okay? So just remember, anything to do with the x is backwards from what it would be with the y. Backwards from what you would think it was. Okay? So let's compare the graph of each function with the graph of f of x is equal to absolute value x. Okay? And let me get my pen back to black. All right, I'm going to put my x-axis way down here this time because I know since there's no negative signs in here, the absolute value is always positive. So help me first. Okay, help me plot f of x equal absolute value x. Give me some points. Second? 0, 0, good choice. Next? Excuse me. Another one? Second? 2 what? Need an ordered pair. If x is 2, f of x is 2. Okay, so 2, 2. That would be right here. Give me another one. Second? 3, and what would the f of x be? 3. Okay, perfect. Next? Negative 3. What would that be? That would be positive 3, exactly. Negative 2 would be positive 2. Negative 1 would be positive 1. Positive 1 would be positive 1. 4 would be 4. Negative 4 would be 4. 5 would be 5. Negative 5 would be 5. Negative 6 would be 6. 6 would be 6. Okay, you got the general idea? Here we have our absolute value function. That's not very pretty, but it's sort of there. That's supposed to be a straight line. Okay, I don't do straight lines too well. Okay, there's our f of x. What do you think? I need a new color for h. Pick me a color. Yellow. Okay, that's going to be hard to read, but we'll see. What do you think 3 times absolute value x would be? Second? Yeah, everything would be all your y values, which is what this is, multiplied by 3. 3 times 0 is 0. 3 times 1 is 3, so that would be up here. 3 times 1 here would be 3, that would be up here. 3 times 2 here would be 6, which would be somewhere up here. And 3 times the 2 here would be 6, somewhere up here. And then 3 times 3 would be 9. I think we're basically almost off scale by then. Okay? So this is what our vertical stretch by 3. Everything is... Remember, y'all probably never played with those little toys that had elastic bands on the thing, and you pulled it and then the arms went up, or, you didn't do any of that. Okay, never mind. Way back in the old days. Hey. All right. How about 1/3 f of absolute value of x? I need, say again? I can't hear. Yes, you're absolutely right. And what color you want it to be? Second? Purple. All right. Okay. Now, 0 would be 0. What your y equal 1/3 here, y equal 1 here would be 1/3 there. And a 1/3 over here. Y equal 2 here would be a 2/3 here. And a 2/3 there. Okay? Y equal 3 here would be 1 now. And this 3 would be 1. Every y value, you do 1/3 of it. What was a y value for your f of x, that's going to be 1/3. So you're absolutely right. It is, you can think of it as wider, but you can also think of it as an elephant sat on the first V and, flattened it out some. A vertical shrink. You don't think that way. Okay. Good for you. Okay. Only weird people think that way. Okay. So, you see how that works? Good deal. There is a checkpoint right after that. Please go home, do the checkpoints. It's not an absolute value function, it's a squaring function. Okay, now that was example 4. Oh, let's see how they did it. I think I need to erase this so you can read what they do. Not that this isn't prettier than theirs, but I don't want to show them up. Okay, here's what we do relative to the graph of absolute value x, which is your gray graph here. Your 3 times absolute value x is a vertical stretch. All your y values are multiplied by 3. 0, 1, 2, all multiplied by 3, so it's a vertical stretch. Make sense? If the c is between 0 and 1, that means it's smaller than 1, now it's a vertical shrink. And again, your f of x, absolute value of x, is the gray, and then when you do 1/3 that, you get the one that's been set on. Okay? Vertical shrink. Okay. Good deal. Any questions on that? Not quite as pretty as mine, but close. Okay. Now, whoa, they skip example 5 and everything. Oh, I think that's it. Oops, let's do example 5 here. Now, if you're very disappointed that example 5 is not on the slide set, take heart, because it is at larsonprecalculus.com, so you can go to that website. No code required, no access code, for absolutely free. Go to the website and see and hear an interactive version of this type of an example. So compare the graph of each function with the graph of f of x is equal to 2 minus x cubed. Boy, they sure picked one. They did the easy one on the slideshow, and then the much more complicated one, a little more complicated, on this one. So here's our basic function. F of x is equal to 2 minus x cubed. That is an interesting function to start with, isn't it? Because to graph that, you almost have to graph x cubed and then do what to it? Reflect it across the x-axis and then go up 2. Okay? Just don't say yours. Okay. So, let's do that. Now, it's going to get really a little messy, so I'm going to draw something first and then wind up erasing it. Okay? All right. Let's first do x cubed. What color you want x cubed to be? Second? Red. Okay. Back to red. Okay, this is red. That's that's red. That's called dark red. I'll do light red. Okay. Let's do x cubed. X cubed in red. What would be some points on x cubed? Oh, let me plot some points here. I should have done that in dark. Okay. 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 Let me go back to red now. Okay. Now, give me some points. X cubed. Second? 0, 0. Okay. Got that one down. 1, 1. Right? Cube 1, you get 1. Right? 1 times 1 times 1. And negative 1 gives you negative 1, because negative 1 times negative 1 is positive 1, but then by another one is negative 1 again. 2 would give you 8. Okay? It's way up there, and it's red on red, so I can't see it very well. And this would be negative 8, which is way down there. Okay? So here's what that function looks like. Something like that. We've seen it before, right? Okay. Maybe not flat enough in the middle. Somewhere like that. Okay, but then we do add 2 to that to give you this. Oh, no. We got to negate it. So give me a color for negating it. Purple. Okay? Negating it would be 0, 0. It didn't go to purple, did it? Okay. 0, 0. But then the plus 1 would become a minus 1. The minus 1 becomes a plus 1. The minus 8 down here becomes a plus 8. Now you might be able to see that one better, but the plus 8 goes to minus 8. You can't see that at all. So here would be the negation of that. So that's with the minus sign on it. Okay? So for right now, I'm going to erase my red. because ooh, it didn't erase, did it? Okay. Erase the red. Okay. I can't get all that. Oh, I did too, didn't I? Okay. And somewhere up here there was red, but I can't see it. Okay. Now, we don't quite have our F yet, but now we're ready to get our F. What does F do to this minus x cubed? Adds 2 to it, right? So we go up 2. Now this, my F is in black, so I'm going to go back to black. So the 0 goes to 2, the 1 goes to 3, the negative 1 goes to positive 1, everything else is off scale, so it does something like this. Something like that. So now I'm going to erase my purple. Is that okay? Okay. Because this should be our starting point. Okay, good. Oops. Left the purple there. All right. Now, what they ask us next is, that gave us our not parent function, that's our f of x. Now what we're going to do is g of x, and what color you want g of x to be. That's why I erased the others, so you can reuse them if you want to. What color you want g of x to be? Blue? Okay. I'll go with dark blue. So your g of x is now going to be f of 2x. What happened? Oh, okay. I think I know what happened there. Okay. Good. Okay. F of 2x. What in the world is that going to be? Any ideas? What does multiplying your x by a number greater than 1 do for you? It's what? Okay, it will, that's what it will become, but what does it do to the graph? It's what? Okay, he's still on y's, aren't you? Y's do that way, x's do the opposite way. It shrinks it because it's greater than 1. Remember that. So, and it shrinks by a factor of 2. Now we're dealing with the x's now. Here the x is 0. Let me get, am I still in blue? I think I am. Yeah. And 0 divided by 2 is 0. Okay, so that's fine. This 1, that goes to 1/2. It's shrunk by 2. The y doesn't change, it's only the x's that change. Here it's a -1, shrink that by 2, and you get a -1/2. And this one up here that was a, yeah, you can't see any of them, all those are shrunk by 1/2. So now it comes down like this and goes down like that. That's what the g does, a horizontal shrink, because you're multiplying by a number greater than 1. Remember, everything dealing with x's is backwards. All right? We're going to do a h next, so I need a color for h. Say again? Red. Okay, we're going back to red. Better red than dead. Okay, never mind. Okay. And the red is the h of x is equal to f of 1/2 x. Okay, what does that indicate you're doing to your f function? Second? Oh no, remember it's doing it to the x. So therefore it's a stretch. Yeah. Remember the x is always backwards, okay? Think of it as left-handed. No, don't think that way. Okay. Now, and we look at our parent function, the black function. So the 0, when you stretch that by a factor of 2, inverse of 1/2, 2 times 0 is 0. So that's still right there. 2 times your 1, though, you're looking at the x values. 2 times 1 would be 2. So now it's stretched out to there. Same y value, the stretch is on x. Okay? And when you had a -1 here, that stretches to be a -2. And then your one up here would stretch also, so your graph does this kind of nature. Maybe not quite so sharp there. Okay. That's what it's doing, a horizontal stretch, because you're multiplying by a number between 0 and 1. A horizontal shrink would be multiplying by a number greater than 1. Yes.
One half is, it contains a fraction. Is that why it's a stretch? I mean,
Okay. That's a very good question. Okay. Now, notice what I said, it went to 2. What happens if you put x equal 2 in this? Okay? If x is 2, 1/2 times 2 is 1. And that would be alpha of 1, where your alpha of 1 was 1. So you see, you've got the same alpha value, but now you stretched it out that way because you're doing 1/2 of x. So basically, you moved your x further out. When you're doing 2x here, that shrinks it in here because 2 times 1/2 is 1. So you get the same value there. So that's why x is backwards. Okay? Because you're multiplying the small number by the x, but you have to have the same y. So that's the, if it's a small number, a stretch, a large number, a shrink. Backwards, but true. All right, the answer? All right, good deal. Good question, by the way. All right, that was example 5. There is a checkpoint with it. Please do the checkpoints, okay? There is a summary at the end of the section, and then there's our vocabulary, which we all look forward to, don't we? Okay, horizontal shifts, vertical shifts, and reflections are blank transformations. What kind? Rigid transformation, okay. You didn't catch that, did you? Okay, never mind. Okay, good. All right. Rigid transformation. A reflection in the x-axis of the graph y is equal to f of x is represented by h of x is equal to blank. What would that be? Negative f of x, exactly. That's what a reflection in the x-axis would be, a negative y, negative f of x. While a reflection in the y-axis of the function of the graph of y is equal to f of x will be represented by h of x is equal to f of negative x. If you're reflecting on y, negate the x. If you're reflecting on x, you negate the y. Good. Number 3. A non-rigid transformation of the graph y is equal to f of x, represented by g of x equal to c times f of x, is a blank blank when c is greater than 1. So I need to write that down because some of you don't have books. Okay? Let me delete what we got here. I know that's a lot of verbiage. Whoa, let me get my black back. Okay. All right. Now let's see if we can get that down. A non-rigid transformation of y is equal to f of x. Non-rigid transformation of y is equal to f of x represented by g of x, g of x equal c times f of x, okay, is a blank blank when c is greater than 1. So if your parent function, your original function is y is equal to f of x, and then you have some g which is c times f of x, what is that when c is greater than 1? So what? It's one kind of stretch, okay? Yes, vertical stretch, because you're doing it to the y value. A vertical stretch. Okay, you can fill in the rest of the letters, right? Vertical stretch. Okay? And a blank blank when c is between 0 and 1. And a blank blank when c is between 0 and 1. What's that? A little louder? Vertical shrink, okay? That means a psychologist who stands up. No, that's a different kind. Okay. Stands up. Cut it out here, okay. Now, Let's do number 4. It's matching. And I think I'm going to have to clear the screen because some of you don't have books, right? So it's hard for you to see what's in the book if you don't have a book. Okay. Here we have A through D. Okay. This is h of x is equal to f of x plus c. H of x is equal to f of x minus c. H of x is equal to f of x plus c, and h of x is equal to f of x minus c. Okay? And rather than write this down, I want you to tell me what that transformation is. Say again? Okay. What are you adding it to? Huh? Okay. What are you adding it to? F of x, right? Is it f of x? You're adding the c to f of x. And what is f of x? Y. And where is y? Yes, it's vertical. So this is a vertical shift. Exactly. Vertical shift. Okay? Which way? Oh, and by the way, C is positive. C is greater than 0. Vertical shift. Which direction?
Oh, so the left.
No. Okay, vertical is not right or left.
Oh, it's up.
Up. Okay, this is up. Very good. What's B? A vertical shift. Down. Okay, because C is positive, but you're subtracting it, so you went down. Okay. Okay. What is C? That's positive. Oh, no, what is A? It's what? Okay, horizontal shift. Left, exactly, because everything's backwards in C with X's. And D is horizontal shift to the right. Fantastic. Right. Okay, good. All right, there's our vocabulary. Aren't they fun? Okay. Homework exercises, do either 5 or 7 or both. They're at calcchat.com. Do number 9. It's at calcchat.com. Do either 11 or 13 or both. They're at calcchat.com. Then do any of the odds 15 to 19. They're all at calcchat.com. 15's those at calcview.com. A little more interaction on those. Okay? Then do any of the odds 21 to 37. They're all at calcchat.com. 21's at calcview.com. And the free websites. No access code needed. Okay? Then do any of the odds 39 to 45. They're all at calcchat.com. However, 39's also at calcview.com. Then do 47, or any of the, either 47 or 49. They're both at calcchat.com. Then do any of the odds 51 through 55. They're all at calcchat.com. Then do either 57 or 59 or both, and they're both at calcchat.com. 61 is a pretty good problem. Take a look at that. You can do that one if you'd like. It should be at calcchat also. Then there's a couple true false, 63 and or 65. They should be at calcchat. Then there's going a little bit extra here, so give it a shot if you can. Any of the odds, well, do 67. Now, 69, I really don't care for because one thing is wrong, you know, and they have the big red X there telling you it's wrong, but it's trying to find the error in it. I don't like for them to show you things that are wrong because I'm afraid that gets planted in your mind and then you think wrong things, think wrong thoughts. Okay, so try number 71. That's a good problem, and that's it for 1.7. All right. Oh, man. All right. Are we going to have time to do... Okay. See, they did try to save the other one, and I said no. So, okay. 1.8. We got 4 minutes. Let's do as much as we can in 4 minutes. I knew y'all would be happy not to waste 4 minutes of your tuition dollars. Okay? I would feel terrible if I squandered it. Okay? Already lost too much with the projector, but that was neither here nor there. Yeah, it was here. Okay. Maybe PowerPoint's going to take 4 minutes to open. We'll see. All right, here we go. Let's get the slideshow from the current slide, and we'll... Okay. Functions in the graphs. As you can tell, this author loves graphs. 1.8 is combinations of functions, and one other kind called a composite function. You're familiar, I'm pretty sure, with combinations of functions, okay? It's stuff we've already done. You've done all your life in math. Composites, though, are a little bit new. So what the combinations are simply adding, subtracting, multiplying, and dividing functions. Yes, we probably can handle that with no problem. Find the composition of one function with another. That's a little bit of a new concept. Not hard, but just a new concept. And then we'll use combinations and compositions of functions to model and solve some real-life type problems. Oh, that will be fun. Okay. So let's look at the arithmetic combinations of functions. Okay? Just as any two real numbers can be combined by the operations of addition, subtraction, multiplication, or division to form other real numbers, two functions can be used, combined to create new functions. Okay? Now, here's an example. Pretty simple one. F of x is equal to 2x minus 3, right? G of x is equal to x squared minus 1. Can we combine those in a sum? F plus g? Sure. 2x minus 3, that's F, plus x squared minus 1. That's the g. And when you combine those, here's a square term, x squared, nothing to combine it with. A linear term, 2x, nothing to combine it with, so that's added to it. But then you have two constant terms, minus 3 and minus 1. They add to be minus 4. There's your sum function. Right there. Pretty simple. I can't imagine you would have expected anything else, right? Straightforward. Okay, how are we doing? Still got a minute or so? Okay. Now let's do a subtraction. Same two functions, okay? Have to be careful here. And this is why it's really important with subtraction to put at least the second one in parentheses. Doesn't hurt to put them both in, but especially the second. Because you see here your quadratic term is now a minus x squared. This is still plus a 2x, but now you have a minus 3 minus a minus 1, which is plus 1, which is minus 3 plus 1 is minus 2. So there's your difference function. A new function is just a difference of the other two. And multiplication is just about as simple. F of x times g of x is f of x times g of x. This one you can FOIL, okay? 2x times x squared is 2x cubed. Now I'm going to not spell it right. Minus 3x squared minus 2x plus 3. There it is. There's the problem. Now here is where you have to be careful. When you're dividing two functions, okay, especially if there's a variable in that denominator, what can the denominator never be?
0.
0. You can never divide by 0. So now you have to watch out. Your domain may have changed. See, the domains of all these did not change at all. They were all real numbers everywhere. Here, you have to exclude x equal plus 1 and x equal minus 1. So both of those will make the denominator 0. So you can't have x written plus or minus 1. Every other x is just like this, 2x minus 3 over x minus 1, as long as x is not plus or minus 1. That's the only difference with division. You have to make sure that denominator is never 0. Okay? The rest of it didn't matter at all. You can add, subtract, and multiply zeros anytime you want to. Don't divide. All right, I'm afraid that's probably it, isn't it? All right, we will begin next time with domain. So, good deal. Have a great weekend. And by the way, be working on your papers and your quiz, right?
Can I have one of those, please?
Oh, let's see. I don't know. Have you been a good boy?
No, I've been trying to be a good
Oh, well, I don't know. That's not good enough. Okay.
See you Tuesday.
All right. Take care.
So,
What's that?
I live in Alabaster, so
Oh,
the
wow.
traffic trying to get here,
Yeah.
they're working on the interstate.
Oh, yeah. There's the quiz. You need graphics? Okay. Get the time zone. Oh, I've got some in here somewhere. All right. Have a good weekend. Take care.
Thank you.
All right. Good deal.
See you Tuesday.
Take care. See you this afternoon. Well, sometime this afternoon. All right. Take care. Take care. Have a good weekend. Your compatriot left early this morning, huh?
Oh,
Oh, I know what it was. Oh, I was going to take that. All right, that's what we'll pick up next time. Still going okay?
Just going, yeah, I'm grasping, but I got to study.
Right.
Understand.
Yeah. Yeah, math almost requires it. Well, it's a lot like it's a terrible example for me, but I took piano for about 3 years and never was any good at it, and one of the main reasons was I didn't practice it. That's right.
Now, I got to be honest, I've never been good at math either.
Right.
For me, really paying attention to it more, I'm beginning to see it. It's not just art, it's just remembering what you need to do.
Yeah. It's a whole framework. Yeah, that's right.
Yeah.
You're absolutely right.
Well, I'm with you.
Oh, I think you're doing well.
All right.
All right. And you're asking good questions. That's the mark that you are thinking well.
You have a good week.
You too. Thank you so much.